This is question 5, and in this question, you're modeling the height of the tides. You know that low tide occurred at 8:30 a.m., high tide at 3 p.m. We know that the maximum is 12 inches above the average. Low tide is 12 inches below the average. F of t is a function of the height above or below the average. So right off the bat, this gives you your A. So A is equal to 12. B is 2 pi divided by the period. We know that low tide occurred at 8:30. High tide occurred at 3 p.m. That is half of a period. And this is equal to 6.5 hours. Therefore, the entire period would last 13 hours. C is gonna be the phase shift. So to do this, it is a good idea to also look at part B, where we are asked to sketch the function. Where are we right now? So we know that at low tide, at 8:30 a.m., we are at the minimum. At 3 p.m. or 15 hours, we are at the maximum. So it should look something like this. At another period, it's going to go down. Then it doesn't have enough time to go back up. So it can probably stop somewhere around there. Maximum is 12, minimum negative 12. When t is equal to 0, we should start over there, essentially. C measures the phase shift. How much are we shifting, are we deviating from the maximum point? This is the maximum point, and remind yourself of the curve of the cosine function. So we start at the maximum. In this case, we can see that we are shifting 2 units to the right. In other words, this guy, the bt plus c part, is effectively 2 pi by 13 times t minus 2. Because we're shifting 2 units to the right. Therefore, c has to be 2 pi by 13 times negative 2, or negative 4 pi by 13. In part C, you know that the species is most plentiful when the water level is increasing. And just by looking at the curve, we can already identify the intervals on which it is increasing. At 7:30 a.m., it is decreasing. At 10:30 p.m., or at 22.5 hours after midnight, it is increasing. Therefore, you should fish at 10:30 p.m. as it is increasing. This is the end of question 5. Question 6. This is an induction question, and you're introduced the duple factorial. Same as any other induction question, we'll always start with a base case. when n is equal to 1. If n is equal to 1, left-hand side is equal to 1 using a definition. Right-hand side, zero factorial is equal to 1. Therefore, the base case is true. You have to show your work explicitly, aka at a bare minimum, you have to mention this on your exam. Otherwise, you will not get the mark for the base case. Step 2. Assume that the statement is true for n equals to k. This is also called as the induction hypothesis. In other words, we are assuming that k double factorial is equal to k factorial divided by 2 to the k minus 1 divided by 2, k minus 1 divided by 2 factorial. Now we'll consider the case n equals to k plus 2. Now you might be wondering, why is it plus 2 here? Because this double factorial is only defined for odd integers. Every single time we are moving up 2 units, 1, 3, 5, 7. It is not n equals to k plus 1. So, k plus 2 double factorial, using the definition, this is equal to k times k times k plus 2 minus 2 double factorial. Using the induction hypothesis, we can simplify our expression a little bit. Where do we go from here? Oh, this should be k plus 2. It's always a good idea to remind yourself of where you're going to. In this case, we are trying to prove that this result is true when n is equal to k plus 2. So let's just write it out. So this is what you are trying to prove. Okay, so we need a way to get k plus 2 factorial upstairs. Cool. How do we do that? If we look at the expression so far, we need to multiply the entire fraction by k plus 1 divided by k plus 1. Because that would give us the k plus 2 factorial upstairs. That also brings us one step closer to dealing with downstairs. The next term of this factorial is going to be k plus 1 divided by 2 factorial. And to get there, we have to multiply the denominator with k plus 1 divided by 2. We already have k plus 1. So what we can do is divide this by 2 and multiply it by 2. And now you have successfully arrived at the printed answer. Hence, by mathematical induction, if pk is true, we proved that pk plus 2 is true. P of 1 is true. Therefore, it is true for all odd integers k. End of question. So this is a rather tricky induction with the factorials. And if you don't write out what you're trying to prove, it can be very intimidating. Question 7. You're given a graph. Part A. Sketch the graph of this, clearly indicating the equation of an asymptote and the coordinates of a stationary point in terms of A, B, C, D, and or E. Sure. How do we get this graph? We get this graph by reflecting of the parts that are below the x-axis over the x-axis. In other words, this part will go up, this part will go down until point E. So let's say E is somewhere over here. It's going to go down, and it's going to go back up. Don't forget to reflect the slant asymptote as well, because it's also going to be part of the transform curve. This line is y equals to minus a minus bx. And this part over here is the comma negative e. Part B. Find the number of solutions to this equation. Cool. So, this guy is very intimidating. It's quite scary. However, if you remember that this is equal to that, then it's really not too bad. In fact, all we have to do is factorizing this equation, and it will boil it down to this simple equation. In other words, we want to find the number of solutions to both equations f of x equals to k and f of x equals to a. We know that k is greater than negative e. In other words, it has to be above the turning point. Something like this. For the other one, f of x equals to a. That is the y-intercept of the slant asymptote. How many solutions do we have in total? 1, 2, 3, 4, 5, 6. This does not count because it's an asymptote. Also, by looking at the graph, it seems like A is less than negative E. So we have a grand total of 6 solutions. 2 solutions from here, 4 solutions from there, 6 solutions in total.